They're 215 watt.
215.0 milliliters. What's set up on the center board is the equivalent weight part of the problem. What's up on the right is the ideal gas law part of the problem. Any question on either of those two parts? Because what comes next is the part where you go from the gas law stuff to the equivalent stuff, and that's the step where everybody messes up. So we're going to pause a moment and make sure we're correct on everything else before we get that one step. Question about anything that's on the board right now related to this problem? All right. What's over there is moles. Moles of H2. Equivalence is equal to moles times absolute value of charge, so 0.0084 times hydrogen is a +1, that's right, but you've got diatomic H2. You've got to account for the fact there's two of them. H in a compound would become H+, but H2 as the element becomes two H+, and so your charge there is 2. So moles times 2 solve for X. And you should get something very close to a small whole number, because we know that charge is limited to small whole numbers. No? Yes? What do you get it?
2.
2. Good. Should come out very close to 2. One divided by molar mass gives you 0.0084. That shows you that the 10 and the hydrogen are on a one-to-one basis. Yes, that's a fluke. That won't work all the time. It does work in this particular problem, but it won't work all the time. For example, if that had been oxygen gas, then it wouldn't have worked. Question? No questions means you know everything there is to know about gas law and equivalent weight, and you're ready for any problem I could think of. Yes?
What's the best way to think logically, like when I see this problem, like step by step, like separating it into what I should?
The first thing, I guess, would be what we've got over on the right, and that's do the gas law part of the problem, because that's the stuff that is more formula based. The equivalent stuff is a little bit more abstract than the gas law. The gas law has very rigid formulas, and when you read through that problem, you definitely have a volume, a temperature, and a pressure. And so that would be my approach: is put a label on those, do all your gas law stuff, and then sit down and figure out what you got to do to get to 10.
What's the balanced equation for that?
We're reacting 10. It says with hydrochloric acid, that's HCl. you're told that one of your products is hydrogen gas, so that would be diatomic H2. Your other product you figure out based on charge. We just figured out that the 10 is a 2+. According to the periodic table, what's chlorine? -1. So electrically, we're looking at SnCl2 as the product. So that's your unbalanced equation. But that's all of your appropriate formulas. And then to balance it, we need 2 hydrogens over here, so 2 HCl, that gives us 2 chlorines, which fits, and that would be balanced. Other question?
About this one or anything else?
Well, I guess first of all with this one. Okay, there's not anything. What else?
Can you do number 29?
We want to know what mass of potassium would be reacted by 20 milliliters of 3 molar H2SO4. The first thing to do is unabbreviate your molarity. That's moles per liter. Capital M molarity is moles per liter. That gives us a mole part and a liter part, and the liter part's going to cancel. So setting up the math is going to look like this. We start with our 20 milliliters because that's the number that has just the one unit. 1,000 milliliters is a liter. 1 liter contains 3.0 moles of H2SO4. And dissect that formula in terms of charge. It's a neutral compound, but neutral at what magnitude? Anybody? 2 positive and 2 negative. 2 is, and that's polyatomic, right? So it's balanced out at a magnitude of 2. So 1 mole of sulfuric acid would be 2 equivalents. Equivalence is moles times charge. The charge in there is 2. So we convert moles to equivalents, knowing that the equivalence of sulfuric acid and the equivalence of potassium have to be the same thing. That's always a 1-to-1 ratio. And then we would need to go from equivalence of potassium to grams of potassium. So according to the periodic table, 39.0983 grams is what charge? Positive 1. Is there a question on that one? we're told that the copper oxide is reacting with hydrogen gas, that's H2, to form copper, metal, and water. And they want us to write the balanced equation. We could write the balanced equation right now if we knew which copper oxide we were talking about, right? There's different versions of copper oxide because there's different charges that copper can be. So what's not directly stated here is we need to find out the charging. Because once we find out its charge, we can piece together copper oxide, right? Electrically. And that'll allow us to go the rest of the way. You start out with 2.42 grams of the copper oxide compound. Once the oxygen's removed, the copper weighs 1.93. The difference in those two masses is the amount of oxygen that was in the compound but now isn't. Grams copper, equivalence copper, molar mass, copper, charge, copper. We know the grams copper, we know the molar mass of copper. We don't know the charge, and we don't know the equivalence yet, but we're going to get that from the oxygen. So 2.42 minus 1.93. This is 0.49 grams oxygen.
How do you know if you need to add or subtract them?
By the wording of the problem. I mean, it tells you that this 2.42 is the total compound and the 1.93 is the copper that's left over. So that means the copper and the oxygen have to add up to 2.42. So you just have to kind of read the wording of it and find out what those masses are. So we turn the oxygen from grams to equivalents, and then equivalence oxygen to equivalence copper. 0.61. We're getting 1.6. What? 7? Okay. Neither of those is as close as they ought to be to 2. But they're closer to 2 than any other integer. Correct? So apparently your charge is 2. Question up to that point.
Oh, I see what you did. It's not 2.42 grams of copper, it's 1.93.
Oh, okay. Yeah.
Because mine came out to like 2.0 something.
Okay, that sounds much better. Thank you. Thank you.
Yeah, there you go.
For some reason I
What's
used
the
the
difference?
pacifier.
Okay, that's, yeah. Easy mistake to make, all right? I plugged in the 2.42 grams of copper oxide, not the 1.93 grams of copper. Everything that goes in that equivalence formula has to be for the copper. So I goofed. 1.93 divided by 0.061. Oh yeah, much better. Comes out dead on for 2. Funny how much better it works when you use the right numbers. Question. Comes out to be a +2 charge. If this is your copper and this is your oxide, then this is your copper oxide. You're reacting that with hydrogen, that's diatomic. You form the neutral metal and you form water. And this one happens to already be balanced, where you've got 2 hydrogens, 1 oxygen. But if it wasn't, you would just balance it like normal, like we did back in chapter 1. But that would be your balanced chemical equation. Question. No questions. All right. Good. The gas law part has a lot of set formulas to it. You've got ideal, you've got combined, you've got Dalton's, you've got Graham's law. Graham's law is the one people always forget to memorize. So don't forget to memorize that. Memorize what standard temperature and pressure are numerically. Those sorts of things. Right? You don't have to memorize R. It's one tiny little thing I'm giving you. But if there's no more questions, we will stop here. Very good. Yeah, I mean, it's, you go through a